Water shortages are common across the western U.S. and many regions globally. Field corn is the preferred crop for many irrigated farms in the Great Plains, but many farms don't have enough water to maximize yield on all acres in all years. With increasing demands on water resources, we need to find ways to increase crop productivity. The challenge with grain crops is that yields can drop quickly with reductions in irrigation. ARS scientists in Fort Collins, Colorado tested and identified the optimal timing across the corn growing season to strategically cut back on irrigation. We found that strategic reductions of irrigation during the vegetative growth period during the first half of the season could save 17% of the annual water used by corn without reducing yields, which means increased productivity, increased crop per drop. These data also show that yield drops very sharply if full irrigation during the vegetative period is followed by shortfalls in irrigation during the grain filling period in the latter part of the growing season. Thus, these results show strategic deficit irrigation can reduce risk to producers if water supplies become unavailable at the end of the season. Finally, we partnered with agricultural economists at Colorado State University to develop and run economic models with this data. We found limited economic benefits from these water savings with current agricultural water and grain prices, but if grain prices recover back even to just 2013 levels, or if water can be transferred to municipal or industrial sectors that pay high prices for water, there are economic benefits to producers. Importantly, strategic deficit irrigation lowered the break-even point for these benefits. Currently, only a small percentage of producers have the flexibility or system capacity to manage irrigation as precisely as needed for strategic deficit application, but improvements can be made with potentially large benefits to producers. Using current grain prices of $4 a bushel in 2019 production costs, we estimated incentives of 350 acre-foot for the 17% of saved irrigation water would increase producer profits by 30% over full irrigation. This research has provided critical information used for planning by producers and water district, among many others. Economic modeling and cost analyses provide guidance on the prices needed for alternative transfer methods and augmented deficit fallow programs under development currently in Colorado. These data and findings also complement programs such as the NRCS Agricultural Management Assistance Programs, which can provide improved irrigation flexibility to make strategic irrigation scheduling possible for even more producers.
This slide illustrates irrigation application technologies that save groundwater and increase crop water productivity, which is the yield produced per unit of water consumed. Irrigated crop production in the southern high plains relies almost exclusively on the Ogallala Aquifer, a declining resource. Although adoption of center pivot irrigation systems greatly increased irrigation uniformity and improved yield and crop water productivity, there are losses from wetting the soil and plant surfaces with sprinklers and from runoff due to wet soil surfaces. This is particularly the case in the hot, dry southern high plains of Texas and western Kansas. USDA ARS scientists at Bushland, Texas, conducted multiple studies comparing subsurface drip irrigation, SDI, and mobile drip irrigation, MDI, with conventional center pivot irrigation methods such as mid-elevation spray application, MESA, low-energy precision application, LEPA, and low-elevation spray application, LISA. Studies showed that SDI had 6 inches less evaporative loss than did MESA irrigation of corn, as shown in the middle figure. The water savings were consistent over 2 years. Crop water productivity was increased 13 to 37%, while yield either held constant or was increased by 19%. Irrigation scheduling for SDI must take into account the decreased water lost to evaporation. So the scientists developed crop coefficients, as shown in the right-hand figure. They found that coefficients were 10 to 15% smaller for SDI than for sprinkler irrigation. These new crop coefficients can be used by irrigation managers. Scientists also compared mobile drip irrigation to LEPA and LISA irrigation of corn for 2 years. The MDI system wets the soil surface only along the line of the trailing drip tubing, as shown in the left-hand figure. Thus, evaporative loss is much reduced compared with LIPA and LISA. The drip tube wets a long distance along the furrow, which substantially reduces runoff losses compared with LIPA irrigation. Yield and crop water productivity were not much different in a wet year, but in the dry 2016 season, the crop water productivity with MDI was 13% greater. Both the SDI and MDI methods allow crop production with more limited well capacity compared with center pivot sprinkler irrigation systems.
Over 2 decades ago, NRCS found that ephemeral gully erosion in the USA accounts for 35% of the total erosion, and it can be upwards of 73%. Worldwide estimates show that it's even higher. In fact, research around the world has shown that gully erosion rates are highest when they first develop and decline with time as the gully stabilizes. ARS scientists have shown that filling in gullies by tillage can reactivate this gully erosion process because it serves to reestablish this high initial gully erosion rate. Research by ARS scientists in Oxford, Mississippi, with collaborations with colleagues in China, have shown that in their black soil region, which is similar to our mollisoils in the Corn Belt, that this repeated filling in of gullies by mechanical operation depletes the topsoil for extensive distances from the gullies and reduces the crop yield by 2% for every 1 centimeter loss of soil. And once the topsoil decreases below 20 centimeters, the loss of crop yield is accelerated. What had not been shown until recently is the impact of this depletion of topsoil on the soil quality as a function of distance from the gully. ARS researchers in Oxford, Mississippi quantified the impact of filling in of gullies on crop yield and soil quality by sampling soil properties in multiple transects perpendicular to the channel. This approach was made on gullies on a no-till field in Mississippi that had been filled in by scraping areas adjacent to the gully with a box blade when the field was converted from conventional till to no-till 5 years earlier. Measurements in Mississippi found that every 1 centimeter loss of topsoil resulted in 3 to 6.5% loss in yield, and areas in which the topsoil was completely removed had essentially a complete loss of yield. The best indicators of soil physical quality were depth of topsoil, available water capacity, and shear strength and soil penetration resistance at the surface. This work guided subsequent work that addressed the dynamic changes in soil quality following tillage as the soil reconsolidated, and it points to the need to include chemical and biological properties to better assess the impact of gully erosion on soil quality.
Under Component 3, Enhancing and Documenting the Benefits of Conservation Practices, we have an accomplishment related to a method for multiple enzyme activities that provides a new soil health index. ARS scientists from Texas and Minnesota developed an assay for multiple enzyme activities on the same soil sample, providing a cost-effective protocol to assess soil health. Soil health is the capacity of the soil to function within its ecosystem boundaries, and the soil chemical, physical, and biological component. Specifically, we want to focus on the biological component and the soil as a living ecosystem that provides so many essential functions to all of us. Specifically, the microbial component and the enzymes they produce are involved in 80 to 90% of the decomposition processes of soils. And any changes in management related to crop types, rotations, cover crops, and organic amendments and tillage practices will impact microorganisms and their enzyme activities. And this can provide indications of changes in nutrient cycling, soil organic matter dynamics in terms of quantity and composition, soil structure, and the capacity of soils to hold more water from precipitation, which is especially important for dryland.
The Southern High Plains region is experiencing a rapid transition to dryland, as the water supply for irrigation from the Ogallala Aquifer is diminishing because of its low recharge rate, which has worsened as droughts and heat waves become more frequent. Examples are the 2011 drought and the year of 2016 that was the warmest year of the planet. And we have studies on how these climatic events have affected the enzyme activities of soils and decreased soil organic matter. We have used enzyme activities to evaluate the integration of livestock into cropping systems for this region to save more water from the Ogallala Aquifer, the use of sorghum as a more drought-tolerant crop for rotations with cotton, and more recently, producers are interested in cover crops under no-tillage practices to improve soil health and be more prepared for future droughts. And we have detected increases in the activities of enzymes within 1 to 2 years of this transition. Although enzyme activities are sensitive indicators of changes in essential soil functions, current protocols are time-consuming because each activity is measured separately. So an assay of multiple enzyme activities on the same soil sample can be used in different soils, climatic zones, and cropping systems. So this new assay will enable producers and landowners to assess soil health and adopt management that increases soil and water conservation.
This presentation is for Improved Auto Irrigation Simulation for the Soil and Water Assessment Tool, or SWAT model. SWAT is widely used to assess the impacts of alternative agricultural management practices in watersheds throughout the world. Simulation results have been used by regulatory agencies for developing remedial measures for impaired water bodies and for water planning purposes. More recently, SWAT has been used to assess the impacts of agricultural irrigation management on water use and hydrologic processes at both watershed and field scales. The default SWAT auto irrigation function consists of two options: a plant ET-based approach and a soil water deficit method. However, many SWAT users have long known of deficiencies of the model's auto irrigation function to simulate cultural irrigation practices, particularly when using the soil water deficit option. Issues included the model irrigating back to field capacity following the triggering of an irrigation event, irrespective of well capacity or irrigation frequency limitations. Another issue is that irrigations would not automatically terminate following a harvest operation. Researchers from the USDA ARS Conservation and Production Research Laboratory and Texas A&M University developed an alternative algorithm based on the management allowed depletion, or MAD, of plant available water, using archived field research data from the CPRL's large weighing lysimeters near Bushland. Datasets included high-quality lysimetric ET and soil water measurements in addition to yield and agronomic data. Alternative algorithm options include 1. A single constant MAD value applied throughout the growing season, and 2. FAO growth stage specific MAD values. However, such detailed crop information is often not available for field scale studies and less so for watershed scale studies. Alternatively, the crop growth stages can be constructed automatically by the partitioning of seasonal heat units generated in the SWAT plant growth database. This flexibility allows users the option to choose whichever method is most appropriate based on available data and specific modeling goals. Additional field scale testing was performed using data from ARS and university research sites in Colorado, Kansas, Nebraska, New Mexico, and Texas. Watershed scale testing was performed using 2 watersheds in the Texas Panhandle. Results included improved simulation of actual irrigation practices, including irrigation magnitude and frequency. Accurate simulation of irrigation is critical for meaningful evaluation of irrigation management strategies and water planning efforts. This work has garnered interest from a corporation charged with the modeling of irrigation in California's Central Valley and from scientists at a university in Germany for aiding with modeling work in watershed catchments. We believe these improvements to SWAT have applicability to other models as well, making for a significant impact on the modeling community.